Good morning, ladies and gentlemen. Thank you all for coming here. I know that cybersecurity is an area of frantic research, and I'm excited to share with you some of the work that my team has done in this area. Also, a big thanks to the organizers of this conference. This is my first time in Japan, and I'm very excited to be here. Let me introduce myself. My name is Bhavna Soman, and I work for Intel Corporation in the United States. My team is called Advanced Countermeasures, Intrusion, and Response. We deal with the advanced adversaries that target Intel. And my specific areas of focus are threat intelligence and data analytics. Today, I will be talking about threat actors and how we can use fuzzy hashing techniques to cluster binaries by the threat actor who created them. In a way, this presentation is about the journey of my team when we were trying to solve a critical challenge in deciphering malware binaries in a short amount of time. Before we continue, I will give you a few disclaimers. The research and views presented here are my own and do not represent Intel. And the other one is just a long-form legalese saying no computer system can be absolutely secure, just Intel lawyers. All right, this is the agenda that we're going to work on today. First, I'll give you some background on why it can be valuable to focus on threat actors to improve incident response, how that can help us improve the process and the defensive stance of an organization. And we'll talk about what we can do, why we want to focus on malware binaries and threat actors. We will look at some algorithms that can be used to connect binaries, and we will see how we can get some data and ground truth to test those methods. I'll show you the results that I got and the sample clusters that we found. And finally, we'll conclude with the takeaways and future direction. All right, so I'm going to talk a fair bit about threat actors today and refer to APT research that has been done by security companies like McAfee, Kaspersky, Symantec, et cetera. But a lot of my peers in the incident response community don't believe in the importance of identifying threat actors. According to them, the only important thing is detection and eviction. I would like to disagree with them. When we talk about attribution, we're not referring to law enforcement style identification. What we're talking about is creating intelligence around actor profiles. We want to identify the motive of an adversary. We want to identify the tools that they commonly use. What are the types of vulnerabilities that they go after? For example, one particular actor group might heavily focus on MS Word or Internet Explorer-related vulnerabilities, whereas another actor might focus on PDF and Flash exploits. So this kind of information can help us identify what are the specific research that the actor is doing and refine our response accordingly. Such information can also help us make strategic investments in our own defense. What are the sort of products we want to install in our environment, and where do we want to invest in our research? And finally, it can help us refine our incident response. Let me share a little bit about how we can do that. How can knowing the origins of a malicious binary give you an advantage in the incident response process? What is the value of connecting a binary to a known bad actor? Can connecting a binary to an actor give you an advantage in your response process? Yes. First, if we can find binaries in our environment that are connected to a threat group that we've previously looked at, then we can apply our existing knowledge about the motivations and the capabilities of that adversary for our response. For example, if I know that a particular attacker is likely to send a phishing message to steal credentials and then attacks the mail server, then once I see a binary from that attacker, I know where to look for next. And secondly, if we can connect the different malware binaries found in the environment to a single actor, then I can build a complete picture of a concerted attack against my organization instead of just seeing random isolated infections. So, how can we make those connections best? that is the question that we were trying to answer in our own team. And automation was a big factor in this. As you all know, malware reversing is a very time-consuming and tedious process. And in the short amount of time that is available for responding to an incident, detailed reverse engineering is not always possible. So what we wanted to do was build a database of APT-related binaries related to actors that we had analyzed in the past, and then have a shortcut to compare a new binary to those methods. We also wanted to collaborate with our industry friends and peers so that we could use the same metric when talking to each other and having conversations such as, have you seen this adversary or this binary before, and can you share information with us about it? So our first candidate in such an algorithm was the Imphash algorithm. It is a pretty simple algorithm. It just calculates the MD5 hash of the import address table of a PE binary. It was proposed by a US company called Mandiant in 2014. And the premise is that threat groups like APT1, they use the same tools and environments to build their malicious binaries. So there is a software development team almost that's sitting there and building all this malicious code, and they end up using the same compilers, the same libraries, et cetera. So a hash of the import address table can be indicative of the binary having originated from the same threat actor. But I ran some quick checks with this method, and it seemed to have few correlations and a lot of false positives. So our team decided to look outside of that method to other algorithms that have been traditionally used to measure code similarity. This group of techniques is called fuzzy hashing, and I looked at two specific algorithms, ssdeep and sdhash. Ssdeep is commonly used in forensic applications. It measures the similarity between two files. Instead of just creating one hash of the entire file, it breaks the file into small chunks, hashes each piece, and then creates a combined hash of the whole file. And then similarity can be calculated by comparing each of the smaller chunks between two files. In fact, there was some interesting research done by an organization called Shadow Server, where it was found that binaries that had a high similarity score using ssdeep were likely from the same malware family. So, and the other method that we looked at was sdhash, and this was proposed by a researcher called Vasil Rusev in 2010. It uses probabilistic feature extraction to extract features that don't occur randomly. It hashes them and puts them in a Bloom filter, which is another probabilistic data structure. To compare the similarity between two files, the Hamming distance between two Bloom filters is calculated. So the idea behind that is that if two files are similar in a statistically significant way, then they were probably created by the same threat actor. Each of these three methods, they calculate semantics in a very different way. Imphash uses equality, whereas the other two use similarity distance. Theoretically, any of these methods could have worked well in connecting APT binaries to each other, but we didn't know which. And to find that out, we had two major problems. The first one was that where can we get a significant data set of binaries related to APT campaigns? As you all know, companies are hesitant to share this data because of privacy and legal concerns. But it also makes it difficult for researchers to get this data and run algorithms on. So that was our first problem. And the second problem was that if we do get a data set of non-trivial size, how do we, for example, if we have a data set of 100-odd binaries, then we have about 5,000-odd pairs of binaries to check. And we can't manually go through all of this data, manually classify each of the correlations as a positive or a negative to conduct any research on it. So this is how we tackled these problems. The first one was gathering the data. So we collected all the APT white papers that were created by various researchers from January to March 2015. We got 25 such research papers, and we used text analysis techniques to extract all the hash strings mentioned in those papers. We even created a small tool that can extract IOCs from several different file formats, and that's on GitHub for you guys to find. So we had this set of MD5s, and we downloaded everything that had greater than 10% maliciousness score from VirusTotal. As you all know, VirusTotal is a popular website that has a huge database of malicious and suspicious files. So now we had a database related to past APT campaigns to test our methods on. And since we know which research paper each binary had come from, we knew which actor it was connected to, which malware family, which campaign, etc. So what we did, we had these binaries, we calculated the 3 similarity hashes, and then we used some Python to make all possible connections. Each method clustered the binaries differently, and the next step was to judge which connections were true and which connections were false. So how did we do that? Here's what we did. Each hash was extracted from 1 or more white papers, and each white paper talks about a malicious actor, malware families, campaigns, aliases, etc. So we manually analyzed this data from white papers and created a dictionary out of them. If the correlated binaries shared an actor, a campaign, or malware family, the correlation was judged as true. For instance, if we know that 2 binaries were used by the same actor at some point, then we can say that they're connected, and the correlation was judged to be a true positive. All right, let me show you the results that we got. This graph plots the recall and precision of the connections made by each method. Recall is the percentage of true positives that was found by each method. And we can see sdhash, which is the blue column, that had the highest recall at 90%. And Imphash, which is the red column, had the lowest recall at 25%. Precision, which is the other graph, that is the percentage of correlations of true positive versus false positives. sdhash had perfect precision at 100%, and sdhash had near perfect precision with only 3 false positives. Let us look at the results from each individual method. First, I'll show you what we got from Impashes. This is the score distribution of the Imphash method. Since import hashes use equality, you can see only 1 score bar at 100. We can see that we got about 580 correlations from this method, and only 408 were true. The true positives were of high fidelity, by which I mean that the binaries that had the same Imphash were very closely connected. They were the same version of the same malware, just different samples. Some of the other things we looked at was whether this method could connect binaries used in the same campaign, used by the same actor in different campaigns. The Imphash had 2 correlations of this type. We also asked if this method can connect binaries that are different versions of the same malware. The Imphash method could not. And we also didn't find any connections where binaries that were used by the same actor in different parts of the kill chain were connected by this method. So these are some of the criteria we had for evaluation. And you'll see that the other methods did a little bit better than the Imphash method. So these are the clusters made by this method. This is a force-directed graph made using a software called d3.js. Each point is a single malware binary, and they are color-coded by the research paper from which they were extracted. This lets us get a visual image of the connections made by Impashes. We can see here that the connections are pretty sparse. There were only 6 clusters with more than 7 binaries. And there were several false positives. Those are the big clusters with the red links. Let me show you these clusters in detail. On the top left in blue, we have 4 samples of Comrat. This was a remote administration tool that was used by the Torla attack group in cyber espionage campaigns against the government entities in Europe, Middle East, and the US. Research has shown that this malware has been used since 2008 in different forms. It was first known as agent.btz and Comrat, and now this same code base has evolved into the Ouroboros rootkit. The samples in this cluster, in this specific cluster, were all version 1.5 of Comrat, and they were all compiled on the 25th of March 2008. And all the 4 samples of this particular malware that were in the dataset were in this cluster. And there were other different versions of Comrat that were present in the dataset, and they formed different clusters using the Imphash method. So while this method can connect binaries that are from the same version, it can't connect across versions. And this is a limitation in the incident response process. So if I get a new binary and I want to see if this is a new version of some malware that I've already seen, then this method won't be able to help me. On the top right, we see the large red cluster, which is a group of samples of a malware called WeepBot. All of these samples had the timestamp of 15th August 2013. And this was used as a first stage dropper by the Waterbug attack group. These were also linked together by the Impashes. Here we have two cases where import hashes matched binaries across campaigns. The samples on the left are both Comrat. One of them was used by the Waterbug group, and the other one is from the Turla campaign. On the right, we have samples of the Carbon malware, which is an intermediate dropper. One of the samples was used in the Project Cobra, and the other one is from the the Waterbug analysis. These are the false positives that were found by the Imphash method. All of the 172 false positives are in these two clusters. In the dense top cluster, we have binaries from 6 different campaigns, including Operation Desert Falcon, the Inception APT framework, and attacks on the Tibetan activists, and a few others. Between all of these campaigns, there is no common link, no attribution, no common malware family used. And these samples were from different parts of the kill chain as well. So somehow they all share the same import hash, which is a false positive. In the lower cluster, we can see samples from 2 different actors. One set of binaries was used as a credential stealer and dropper by Operation Arid Viper and on attacks on the Israeli government. And their import hashes are connected to an attack on the Syrian government. One possible reason for these false positives can be packers. Packers are programs that are used by malicious actors to evade antivirus detection that is signature-based. Since the import hash method looks only at the import table, it is possible that it can be misled by applications using the same packer. We will notice that other methods don't have this drawback. Let us look at the results that we got from ssdeep. This is the score distribution. We can see that we got 856 correlations, which is almost twice as much as what we got from Imphash, and there were no false positives, so that's pretty good. We found one correlation connecting binaries used by the same actor in different campaigns, and there were several instances of correlations between minor versions of the same malware. And there were no correlations where this method could connect binaries used across parts of the kill chain. So we see that ssdeep showed a definite improvement over the Imphash method, but it has some downsides. From the perspective of wanting to create a database of previously analyzed APT binaries and comparing new ones with this method, the Imphash method is relatively easy because you only need to compare or search for the MD5 string of the Imphash through a database. On the other hand, with ssdeep, you have to run the distance function between every 2 pairs of files to determine whether you have seen this file or something similar in the past. And this can have a computational overhead. So this might not be a problem for different organizations depending on your infrastructure, but this is a drawback of this method. This is a graph of the overall connections made by the Imphash method. We can see several large clusters. Let me show you some in detail. I want to point to the large cluster at the bottom that's in blue. That consists of samples of Comrat, which we had mentioned earlier was used by the Turla attackers. With the Imphash method, we saw small clusters of this malware, with each cluster containing only the same version of that malware. Here, we have a giant cluster of across different versions. Here, we have 16 different binaries of different versions of the Comrat compiled over a period of 3 years, connected together by this method through code similarity. So if you're an incident responder looking for information about an unknown binary, ssdeep is more likely to be able to tell you which malware or which past sample is your new sample connected to. These are some more correlations made by the ssdeep method. As you can see, the clusters are significantly bigger, which means that your chances of being able to get information about a new binary are higher. The clusters in green are samples of a backdoor that was used in Operation Desert Falcon that was researched by Kaspersky. There were 680 correlations related to this backdoor that was found in our data set, and the average score was 35.13. And at the bottom, we have 3 binaries connected together. These were different versions of the carbon malware that were used in Project Cobra and the Waterbug campaign. This was an example of sdhash being able to make connections between binaries used by the same actor in different campaigns. And as I mentioned, there were no false positives that were found by sdhash. All right, let's look at sdhash. That's the final method. This is the score distribution for sdhash. This was the method that gave maximum correlations, about 1,400, and had only 3 false positives. Empirically, we set the threshold at 10, so all the connections with a score of less than 10 were disregarded. This method found connections between binaries used in different campaigns by the same actor. It was able to find connections between different versions of the same malware. And it was able to connect binaries used in different parts of the kill chain. On the flip side, it has the same drawback as ssdeep. If we want to create a database of known binaries and compare a new one against that, we have to calculate the distance between every pair of files. Additionally, ssdeep generates a hash, which is though longer than an MD5 hash, it is still of limited length. Whereas sdhash generates and stores Bloom filters, which are significantly longer. Their length is typically about 2 to 3% of the input file. So that can, again, be a drawback depending on the infrastructure that's available at the organization. These are the clusters that were found using sdhash. We can see that they are way denser and have more overall connections. These are the clusters that I found most interesting that were created using sdhash. The larger red cluster contains of 30 different samples of the Ouroboros rootkit compiled over a span of 3 months in 2013. And the second cluster on the right, that's really nice. The samples in purple are the dropper, the stage 1, stage 2, and the injected library of the Cobra system, described to be used by the Turla attackers. And the samples in red are those used by the Carbon tool used by the Waterbug attackers. There has been some research that suggests that Cobra and Carbon are actually just one malware framework with various plugins that can be used to generate binaries for different parts of the kill chain, for different parts of the attack. And the sdhash method was able to identify enough code similarity between those binaries that have different functions to link them to each other. So in the incident response process, that can be a very useful tool to have. And this was done by the sdhash method only. This can also help people in a forensic investigation to build a better timeline of an incident. These are the false positives that were found in the sdhash method. One connects a backdoor used in Operation Desert Falcon to the scanbox tool that was used in the Anthem attacks. And the other one is another binary from the Anthem attack that got linked to the Carbonac APT. There is no known link between these 2 binaries. So this is just a false positive. All right, so we looked at the results of the evaluation and the clusters generated from each method. So what is our conclusion? I started this discussion with a high-level strategic question about why we want to connect binaries to threat actors. And then we did a deep dive into the technical methods. Now let me come back up again. The goal of this research was not merely to find which method is best for connecting binaries. What we really want to do is engineer systems and algorithms to do this for us. We want to be able to visualize the actions of an adversary and thereby simplify the process of investigations and incident response. This talk is really about automation. We want to create a lookup table for the tools that bad guys use. Our big push is to set up such systems. We have seen various research that threat groups constantly reuse their tools. They create new versions of the malware that they have used in the past. In fact, there was an excellent paper by FireEye that talked about how 11 different targeted campaigns had used tools created by one single group of toolsmiths. So code similarity can be an excellent way to connect tools to attackers. And lastly, it is important to know your adversary. If you know that, you know where to focus your intelligence efforts. You can monitor for all data about their tools and tactics. You can learn about the types of vulnerabilities they go after. And that can help you make strategic investment about the defense of your organization and not just chase the next infection. That is all I have for you. I would like to thank my colleagues Jeff and Chris for guiding me in making this presentation. And I would like to thank all security researchers who do APT-related research, particularly Kiran Bandla of Arbor Networks, who is the maintainer for APT notes. And lastly, I would like to thank VirusTotal that have made their data available free of charge to security researchers. My email address and Twitter handle are up there if you want to share ideas, comments, thoughts in the future. And with that, I open the floor for questions.
皆様何か質問を受け付けておりますので、どなたか今の内容についてご質問がありましたら手を挙げていただけますか。はい、真ん中のブロックの前から3列目でございます。今マイクをお届けいたしております。
Hello. I have two questions. The first, you mentioned and you use APT malware in your slides. I want to know if this method can be applied to other malwares as well. And the second question is, I think the three methods you mentioned in this talk only apply to they are static ways to correlate malwares. But we know that there are some malware who were written in shellcode, which can be obfuscated easily. So regarding this kind of malware, do you have other methods to do correlations?
Thank you for your question. Let me answer the first one first. You asked if these methods will also be similarly applicable to non-APT related binaries. And while I have not done the data analysis behind that, my estimate would be that that would be true. Also, there is some past research done by Shadow Server which looked at the sdhash method specifically, and it said that if two binaries have a high score in sdhash, then they are likely from the same malware family. So yeah, some of these methods might help correlate based on malware family for different for crimeware related binaries. And your second question was if there is shellcode or some other, something that we cannot statically analyze. These methods, they look at the byte pattern of the file that is recovered in the case of an investigation or an incident that is live. So if you think that those types of attack vectors have a byte pattern which can judging the similarity of which will be helpful to us, then yeah, we can use these methods for that also in a limited sense.
But for the second type, I mean those shellcode malwares, they can be easily obfuscated using simple encoding, for example, just XOR or a byte shift, something like that. So I don't think this method does well on this malwares.
So the obfuscation part is valid for all different types of binaries. If a particular threat attacker decides to use a new method of obfuscation, something custom perhaps, or encryption, then none of these methods will work in that case. And that holds for smaller files as well, or any other type of byte, because that byte pattern will get obfuscated, and then these methods will not work in that case.
Okay, thank you.
ありがとうございます。他にご質問ある方いらっしゃいましたら手を挙げていただけますか。どなたか、はい。では、前から 2行目の方にお願いいたします。
今回これ、分析の対象がマルウェアということなんですけども、もっと範囲を広げてその正しい実行ファイルですとか、ありとあらゆるものをこのハッシュにかけて分類した場合っていうのも、有効に分類ができるようになるものなんでしょうか。
What is the other thing that you're talking about analyzing with these methods? Executable files of a different format? I didn't understand.
いや、例えばその Windows の中に、こういう APT ファイル入れといて、それでその全ての、もの、例えば DLL のハッシュを取った場合にその、クラスターができるわけじゃないですか。でその際にちゃんとそのマルウェアのクラスターとその Windows の元からあったもののクラスターときっちり分かれたりするものなのかなどうかなっていうようなところをちょっと今回のプレゼンの範囲からちょっと広げた感じの解析をしたときにどうなるのかということをお伺いしたいと思っているんです
けど。So if I understand your question correctly, you're trying to ask if these methods can be used to differentiate between non-malicious and malicious files. And methods like ssdeep have been used for that, but the false positive in that case is much higher than what we found with this. Because here we have the starting assumption that the file is malicious. When we were getting these files from VirusTotal, they already had a maliciousness score of more than 10%. So if you want to apply this method in real life, one would have to have some checkpoint or some heuristic to judge that the file is malicious, and then these methods can be used to cluster either by malware family or by APT threat attacker. Simply to use this method for judging malicious files versus good Windows files would result in high false positive. Did I answer your question?
はい、それでいいんですけど、その偽陽性の率っていうのが、どれぐらいになりそうかっていうような、その例えばその判定するに対して、実用的かどうかっていうところに関してなんかちょっと印象で結構ですので、知見があれば教えていただきたいと思うんですけど。
Yeah, you're absolutely right, and that false positive rate, in our experience at least, has been very high, which is why we don't use these methods for differentiating between malicious and non-malicious binaries. If we could do that, then this would start acting like another antivirus product, and that is not what we're trying to do here.
どうもありがとうございました。よくわかりました。
ありがとうございます。他にご質問ある方いらっしゃいますか？今日はラッキーなことにまだ質問時間がたっぷりございますのでどうぞお気軽にお手を挙げていただければと思います。どなたかいらっしゃいませんか？はい、では左のブロックの後方の方にマイク今お届けいたします。
Thank you for your sharing. I just have a simple question. If I were an attacker and I would like to reuse my code, could you any suggestions about how to break this mechanism? Thank you.
That's an excellent question, and a lot of this research is based on the fact that APT threat actors, they're often companies and they're like enterprises, and because they don't want to reinvest the time that they have spent in building one piece of code, and that is why they continue modifying it and creating different versions, because that's a hard job to create good rootkits. And that is what we're playing on. If, for instance, one APT group had a lot of resources and they decided to scrap their old code base and start anew, the byte pattern similarity would cease to exist and these methods would fail. These methods are not doing a dynamic analysis of the functions or the actions taken by the binary on a host or on the network. They are literally analyzing the byte pattern, and those rely on the same code base being used again and again. So if you were an attacker and you wanted to work around this, you would have to create your rootkit or your dropper from scratch.
Okay, thank you.
ありがとうございます。他に質問ある方いらっしゃいましたら手を挙げいただけますでしょうか。できるだけ見えるように手を大きく上げていただけたらと思います。いかがですか。それではですね、第1回目のセッション、これにて終了とさせていただきたいと思います。もう一度、Bhavna様さんに大きな拍手をお送りください。ありがとうございました。